This is a recording for section 14.1, Graphs, Paths, and Circuits. So this first chapter has to do with graph theory, but not your traditional graphs that you think of where there's an XY axis. We use graph theory to find, for example, the shortest or most efficient routes, like garbage trucks, bus drivers, traveling sales director, postmen or postwomen, or to represent the parent-child relationship for 5 generations of a family, for example, right? But the shortest path, if we think about garbage trucks, right, they have to use gas. So we want them to, go around the city and pick up garbage using the shortest path, right, to save gas money, for example. Graph theory was launched by the Swiss mathematician Leonhard Euler. He wondered whether it would be possible to walk through the city of Königsberg and cross each of its bridges exactly once. And we're going to look at this problem later and answer it. A graph consists of a finite set of points called vertices, or singular is vertex, and line segments or curves called edges that start and end at vertices. So you can see here in this graph here, there's 4 vertices, A, B, C, D, right? But this right here, this AD, that's an edge, right? So you can see that there's also 4 edges, AD, actually more than 4 edges, BD or DB, it doesn't matter how you say it, AC or CA, and BC here. And then there's also this loop here, which is an edge that starts at C and ends at C. So you actually call this edge CC. And says that over here. And again, the edge BA is the same as AB. It does not matter which order that you write it. And when you're doing your homework, it doesn't matter as well in MyLabs Plus. List all the edges in the following graphs. So we have 2 graphs here in part A here. I find it sometimes helpful to trace the edges as I'm writing it down to make sure that I don't forget any. So the first edge is DC, or again, you can write that as CD, it doesn't matter. The next edge here is BC, or CB. And here we have the edge AB. And then we can look at the second graph, and the second graph has 4 vertices and 4 edges as well. 3 edges, sorry. 4 vertices and 3 edges. The first one here is AB, BC, and CD. And it says, what do you notice? So if you actually look at the 2 graphs, DC and CD, those are the same, right? BC, BC, and AB, AB. So what do you notice? They have the same edges, right? And so what we say is these graphs are equivalent. It doesn't matter how you draw out the graphs. So how I might draw out a graph might be different than yours as long as we have the same edge set and vertex set, right? So these 2 graphs, all right, all you really want to show is that AB is connected, BC is connected, and CD is connected, and both of those graphs do that, so these graphs are equivalent. Use the graph above, or I guess in this case below, to answer the following. Give the vertex set V. So we have vertex A, B, C, D, and E. So we'll just separate our answers with commas. Again, you could put those in any order that you like, but you would need to separate them with commas. And be sure in MyLabs Plus, if they're capital letters in your homework, that you put capital letters into MyLabs Plus. Okay. Give the edge set. So again, I'm going to trace them as I write them down so I don't forget any. AB, AC, in any order that you like. BC or CB, CD, CE, BE, BD, and then you have this loop, remember, which starts at D and ends at D, so that's DD. And then you actually have two edges between D and E, DE, and you could write DE again or ED, it doesn't matter, right? But you actually have two of those. So here we are back to this Königsberg problem. In the early 1700s, the city of Königsberg, Germany, was located on both banks and two islands of the Pregel River. The figure below shows that the town sections were connected by 7 bridges. Draw a graph that models the layout of Königsberg. Use vertices to represent the land masses and edges to represent the bridges. So we actually have a right bank, you can see, is all of this over here, right? All that's the right bank. So that's one landmass. And then you have the island in the middle. And then you have this left bank, which is one landmass, and an island. So there's actually going to be 4 vertices, right? Because it says to use the land masses as the vertices. So when you draw it over here, right, it probably helps to kind of put it in the same layout as it is over here. So maybe we want to label right bank, left bank, island 1, island 2, something like that, right? And basically we want to put an edge in if there is a bridge from the landmass to another. Well, let's start with the right bank up here. From the right bank, there's actually 2 bridges down to the island. So when I draw it over here, right, again, I'm drawing a graph of this. There's 2 paths to the island, and from the island to the left bank, there's also 2 ways to get there. So I'm going to put 2 edges over here. Now, if you look, there's this island over here, right? There's actually a path from the island to the other island, but you can also get from the right bank to that island, and you can get from the left bank to that island. So there is a graph that represents this town of Königsberg. And again, what Euler wanted to figure out, as we will talk about in a minute, is can a person walk through the town and walk over each bridge exactly once and start and end at the same place? So that's what we are going to be looking at. So graphs, again, can model many things. Here is another example. It says modeling bordering relationships for the New England states. Draw a graph that models which New England states share a common border. Again, we're going to use vertices to represent the states and edges to represent common borders. Okay, so again, I'm going to draw my graph over here, but I'm maybe going to try to make my vertices kind of match up with where they are in terms of the picture. It looks like New Hampshire's to the left of Maine and Vermont like that, and it looks like sort of Massachusetts is then down here, and Connecticut and Rhode Island. Right. And again, any order that you have the vertices in, it does not matter. It's just, it might help you to put them sort of in the same places. So it looks like, let's start with Maine first. It looks like the only place, the only state that is connected to Maine here is from these states is New Hampshire. All right, they share a border, so we're going to connect them with an edge. And then next we'll look at New Hampshire, and of course we already have that it's connected to Maine, right? We just already did that. But we can also get to Massachusetts and Vermont. So from New Hampshire, we will draw an edge to Vermont and to Massachusetts. You're going to have to just look at each state separately. So I already did this one and this one. So next we'll go to Vermont, and I already have the edge between Vermont and New Hampshire. I already did that one, this one. All right, but then we will connect Vermont to Massachusetts. And so those are the only two edges that should be coming out of Vermont. It's connected to New Hampshire and Massachusetts. And then next we'll look at Massachusetts, and we already have the edge to New Hampshire and Vermont. So let's go down to the other two, connected to Connecticut and Rhode Island. And then lastly, we'll look at Connecticut, which is already connected to Massachusetts, but we need to connect it to Rhode Island. And then we are done because Rhode Island is connected to the other two. So that should be a picture of, or the graph for the New England states. So we're going to look at some vocabulary for graph theory. Something that we're going to be very interested in is the degree of a vertex. The degree of the vertex is the number of edges at that vertex. Okay, so if you look at B, for example, it says here that the degree is 3, and that's because there are 3 edges coming out of B. So the degree is the number of edges at the vertex. So the degree of vertex C is 2 because there's 2 edges coming out. The one thing that you have to be careful of is these loops, because here, if we look at the degree of the E here, 1 edge, 2 edge, but you actually count the loop going both directions, 3 edges, 4 edges. So the degree of that loop is actually, the degree of vertex E is actually 4. Okay. And so we will count the degree, and anything with an even degree is called the even vertex. So if the degree is 2, 4, 6, or 8, those are even vertices. So it looks like in this graph here, D has degree 2, and C has degree 2, and E has degree 4. So those are going to be the even vertices, and the other two have degree 5 and 3. So those are going to be odd vertices. All right. So if it has degree 1, 3, 5, etc., it will be considered an odd vertex. And 2 vertices in a graph that are said to be adjacent vertices if there is at least 1 edge connecting them. So if we look at A, all right, it is adjacent to vertex E because there's an edge here. It's adjacent to vertex D because there's an edge there. It's adjacent to this one and adjacent to this one. So vertex A is actually adjacent to A, E, C, and B. So here we are given this graph, and we are supposed to answer these questions. List the vertices adjacent to vertex A. So, and the other thing I should mention, if there's a loop, it's adjacent to itself. Okay. So list the vertices adjacent to A. Where can you go from A? You could go to C, and you can go to B. Of course, adjacent always means next to in any case, right? So that makes sense, right? Those are the only 2 adjacent to A, right? That there's a path directly to those 2 vertices. And then it says list the edges adjacent to ED. So we're interested in edges that are adjacent to this one, right? So that share a vertex with that, right, next to. So this edge, this is the edge CD, is adjacent. This one as well, EC, and this one, BE. Those are all adjacent because they share a vertex with the edge ED. List the vertices adjacent to vertex C, that's up here, and it looks like C is connected to all of the other vertices, so that would be A, B, E, and D in any order. Right? Adjacent means shares an edge with, so those are all adjacent to vertex C. What is the degree of vertex C? There are 4 edges coming out, so this has degree 4. And this is the notation for that, degree of C in parentheses. The degree of C is 4. What is the degree of vertex B? And again, if you would ever like to pause this video and try to answer the questions and then watch it and see if you get it correct, that's actually a great strategy. The degree of vertex B is 1, 2, 3. 3 edges coming out of B. Is C an even or odd vertex? This does not belong over here. Is C an even or odd vertex? Well, C had degree 4. So it's even, has degree 4. Is B an even or odd vertex? Well, B has degree 3. All right, so it's odd. And then the last question, it says, what is the sum of the degrees of all the vertices? So now we're going to have to write all of the degrees out. B has degree 3, we just decided that. A has degree 2. We already found C has degree 4 edges out of it. D has degree 2 edges out of it. And E has degree 3 edges. And sum, of course, means add. It says, what is the sum of the degrees? So we'll just add up all the degrees. 6, 10, 14 should be the sum of the degrees. Another example, draw a graph that has vertices A, B, C, D, E, and edges, all those listed. And then we're going to be asked a couple questions about the graph. It says draw a graph. It has vertices A, B, C, D, and E. Again, you can put those in any format that you like. I'm just going to put them around a circle maybe. But you could do anything you want, right? As long as your edge set is correct, it doesn't matter what your picture looks like, right? So now we have our vertices, A, B, C, D, and E, and now we'll look at the edge set. The first edge is AB, so I'm going to connect those. AC, BC, BE, BD, DE, another DE. All right, so just make sure those are 2 distinct edges. DD, so that means there's a loop there at D. And the last one is CE. So that is what one graph might look like. And then it says, what is the degree of D? So again, we want to know how many edges are coming out of D. So that's 1, 2, 3. And then remember the loop, you count twice. 4, 5. So this has degree 5. You could also go up here and count in your edge set how many edges have D listed as one of the endpoints, and it looks like 1, 2, 3, and then 4, 5. All right, so you count those, the number of D's listed up there, which is also 5. What are the vertices adjacent to D? Keep in mind that there is a loop. The vertex is adjacent to itself. So again, you can come up here and see which vertices which edges have D listed with them, and then you know that then B must be adjacent. Or you can look down here at your picture, which vertices. Doesn't matter. E, and you don't need to list the vertex twice. What vertices are adjacent to D? B, E, you don't have to write E again, right? And the loop, it's adjacent to itself, and of course C. And you, oh wait, not C. Sorry, that last one wasn't part of the set. Then you go back here and check it. B shares an edge with E. We have that one with B and with itself. Right? So a little more vocabulary. A path is a connected sequence of distinct edges. A trip in a graph that starts at one vertex and ends at a different vertex and has no loop. Okay, so we are going to want to distinguish between a path and a circuit. So a path starts at one vertex and ends at a different one. So if you look at this first example, highlighted in red here, A, B, C, D, this vertex is D, although they can't see it, is called a path of length 3. So you kind of go, okay, this is 1, this is 2, and this is 3. You want to count the edge, not the vertices. So that is a path of length 3, right? There's a lot of different paths from A to D. That just happens to be one of them. You could do a path ACD, right? That would only have length 2. A circuit is a path that begins and ends at the same vertex. For example, A, B, C, A. That's a circuit because it starts at A and ends at A. And again, you count the edges. It has length 1, 2, 3. Example, list another circuit that starts at vertex A to B to E. There's many possible answers here. A, B, E, C, A. Right, that's a circuit. Right, circuits start and end at the same vertex. A path starts and ends at different vertices. All right, this is the last slide in section 14.1. A graph is connected if for any two of its vertices, there is at least one path connecting them. A graph that is not connected is called disconnected, and a disconnected graph is made of pieces that are connected by themselves called components of the graph. So if you look at the first example, A, it has 4 vertices and it is connected because there is a path from every vertex to every other, right? And you can see the difference here between this sort of same graph that's disconnected is here D is off by itself. There's no path to D from A to D, for example, so it's a disconnected graph. This is again connected. This here is disconnected, A, B, C, D, E here, but then this is a separate component. You can't get from D to E, so it's a disconnected graph. So that is the end of section 14.1.